Great. Great. Yeah, happy? Okay. Okay, great, great. Let me start by introducing the global, so IGWIN is a bad acronym. It's the International Gravitational Wave Network. I guess IGWIN network is actually redundant. So when we tend to think about the ground-based interferometers, it's not one or two, but we're really thinking about this kind of collection of observatories, right? So, oh, I've got a mouse, how about that? Yes, yes, okay, great. So of course, so we're really thinking about this kind of collection of observatories, right? So there's two LIGO sites, one up in Washington State and one in Louisiana, both in the United States, is in Italy. And then Geo 600 is a little less sensitive. It's mostly used for prototyping. But then there's CAGRA is actually, the CAGRA sensitivity at the moment doesn't really match LIGO and Virgo. So at the moment, it's really, I would say that of sensitive instrument, let's say sensitive instruments are sensitive enough to like see a binary black hole merger so far. And that's really the two LIGO instruments and Virgo. So there's kind of a 3 detector network at the moment. CAGRA is, they're kind of, I think they're targeting, well, we'll talk about sensitivity in a moment, but they're coming up to speed quickly. And then LIGO India doesn't exist yet, but it's in the plans. It's an interesting story. So there at one time there were actually 2 detectors co-located at Hanford. So there were actually 3 LIGO detectors. That second Hanford detector no longer exists. So what were planned as parts to go into Hanford instead are now planned to go into India. And so there are plans to have construction there and to have a 3rd LIGO site in India. It doesn't exist yet, but here's hoping it goes through. Okay, so I wanted to open with just some imagery just to give some physicality to the detectors. I think kind of the measurement principles were pretty well covered this morning, but I still want to give a sense of just that these are real things that exist. So here's a photograph of LIGO Livingston. It's in Louisiana. It's the southern US. It's a swamp. So photos of Louisiana always look very green. Photos of Hanford always look very brown, right? So there's crocodiles and snakes and forestry. When there's logging in these forests, it causes some excess noise, all those sorts of things. Here's some more photos. So Virgo, I should use the mouse. So Virgo is in Italy. It's near Cascina, which I understand is not so far from Pisa. I've never been, I'm sure it's very nice. LIGO Hanford in Washington State, sort of a desert. So there you go. And then this is a short video clip, again, just to give some physicality to the instruments, just to give them a sense of them. I think there are shots maybe inside. So you can see the long beam tubes, right? The 4-kilometer beam tube. What you see in imagery, concrete outer shell, and then there's the beam tube inside. Metal beam tube. Inside the metal beam tube is under vacuum, it's evacuated. And then there's this concrete shell around just to protect the beam tube from hunters, crocodiles, and things like that. Here's a few shots inside the control room. You can see my friends working on something. I think that's it. Okay, good, good. I think we've probably seen this already. Where'd it go? That's strange. Now it comes. Oh, it's on a delay. That's interesting. That's fascinating. So, all right, good. So I think we've probably seen it before. What I like, there's a few things I like about the particular. So these are 2 merging binary black holes, probably caught on. There's a few things I like about this particular animation. One, this is actually based on simulation data. So this is not an artist's rendition so much as a rendering of a supercomputer simulation by black holes. The other thing that I like about it is that it's star field behind it, right? So this is imagery from a telescope, but it's a simulation data. But what I like is that you can see the star field jiggling. And I think that that's done with ray tracing, right? So this is some attempt to picture what one of these things would really look like, right? And what kind of tickles me is that these stars kind of course, it is slowed down, right? So this, of course, happens much faster. Signals, but this kind of gentle jiggling that you're seeing, that's that perturbation. That's the gravitational wave source in a sense, right? This one is much more of a cartoon, but I like it. But maybe we'll let that one go. But of course, I guess maybe to highlight just that, you know, LIGO's of course been observing, most of the observations by LIGO are of binary black holes, but there's been a few now binary neutron stars, and binary neutron stars, maybe it's worth saying that they have a lot of other thought. Black holes, when they merge, we're just getting signals in gravitational waves because there's no matter, there's no electromagnetic radiation. With binary neutron stars, of course, there's a lot of matter present, things falling out, there's radioactive decay, there's they're growing heavy elements, and you're getting these electromagnetic parts, and in this like cool big explosion. Okay, so let's talk for a moment about sensitivity. Oh, it's like I can predict the future. I love this. So I'm going to show a LIGO noise curve. There it is. I've got mind control from my computer. So what have we got? So, okay, so a few things going on here, some of which may be familiar and some of which may be not. So please bear with me. So first of all, these curves, we should say what's being plotted. So these are LIGO noise curves. So LIGO is a high precision measurement. We're always limited in sensitivity by noise, right? So there's always, the whole game is trying to reduce noise. So at any moment there's noise covering up some signals, and the game is always to lower that noise to try and find those signals underneath. So on the y-axis, this is the amplitude spectral density. So this is a measure of, in this case, you know, the noise. It's more or less the noise calibrated to be in units of strain. That's what it comes down to. And then on the x-axis is frequency. Of course, you can see maybe what maybe the most obvious thing that jumps out is this sort of, oh, the mouse delay is bad. But maybe this thing that sort of jumps out is this sort of shape. So there's a lot of noise at low frequencies, and then the noise rises again at high frequencies, which means that the sensitive band of the instrument is right around here, right around, say, 100 hertz. People talk about, say, between 50 hertz up to about 300 hertz as of the instrument, the most sensitive part. It's maybe the first thing to know about any gravitational wave observatory is that it's only sensitive in some frequency band, just like any electromagnetic observatory would only be sensitive in some frequency band. And then the color codes here show sensitivity curves over different observing runs. So LIGO has been operated in these observing runs, which are, they're like somewhere between 3 months up to about a year long at the moment. And they're just numbered. So O in the first observing run, O2 is the second observing run. So these are counting observing of advanced LIGO. So O1 was the beginning of advanced LIGO. That was 20 when saw the first there. And what happened the whole time, it kind of progressed. Time folks work to find noise source where it, yeah, please.
Yes, I have a question about losses. So I understand that it's very sensitive, right?
Yeah, so yes and no, but I start by saying about line noises. Just noise. Great. Yeah, let's talk about the noise. That's great. So, yes. So yeah, issue. So seismic noise is filtered out by having this is hanging on pendulums, right? So it's a quadruple, and that's high frequency noise, or separating the pendulums from the ground motion at higher frequencies. And so for that reason, the seismic noise is a very steep function of frequency. So it's an issue at low frequencies. It's not an issue at high frequencies. So yes, seismic motion is certainly an issue, and it doesn't even take an earthquake the ground moves all the time at the micron scale, say. So in non-earthquake times, in quiet times, the ground is moving under your feet at kind of the micron scale. Well, remember the micron scale is minus 6 meters, and we're 15 orders of magnitude below that. So ground motion left to its own devices would be a huge, right? You couldn't just set an inch mirror on the ground. It would shake 15 orders of magnitude too much, even when there's not an earthquake, okay? Having said so, yes, ground motion is an issue. There's a lot of hardware to isolate it. So it's a quadruple pendulum, right? So mirror hangs from another mirror, which hangs from these big, I think they're big metal sheets. And so it's like a really good, like, I don't know, junior level physics problem to work out the pendulum response, right? But so that's what it's 1 over f squared, right? It suppresses the ground motion. And on top of that, there's actually active control loops, active feedback loops, which also suppress seismic motion. So actually right now, our seismic control and our seismic suppression is good enough that it's not the dominant noise source. So it is a noise source, but at the moment, it's low enough that you don't see it in this noise curve. At the moment, low frequencies, we're dominated by what's called controls noise, which are kind of the limits of our ability. So is feedback loops on top of feedback loops, right? The whole game is holding those mirrors really still. And so at low frequency, we're actually, at the moment, we're dominated by our limit controls. At high frequency, it's shot noise, so with laser noise, photon counting. And mid-range frequencies, I think limited by thermal noise right now, or at least we hope to be, and where it's limited by thermal noise, which means the molecules on the coatings of the mirrors shake because they have some finite temperature, right? And so there's some of that noise. I don't know that that's quite dominant yet, but that's nearly limiting noise source. Sorry, that was more than you wanted. Did that help? Well, yeah, so it is an issue. So when there's an actual earthquake, like earthquake, I mean, that can break a run, right? That can break a lock. So in other words, if we're observing and there's a large earthquake, then we might have to stop operating for like 10 minutes or something like that. But more often than not, I guess I would say that earthquakes are rare enough that that's not a deal breaker. Like you have to isolate from seismic motion anyway. And so the occasional big earthquake can, delay things. It can cost you an hour, but it's not a deal breaker. But in general, so that's a great question. So it turns out it depends what kind of ground you build your instrument on. So Livingston is built on a swamp. It jiggles around for a while after an earthquake. The Japanese detector is in a mountain, right? And so that actually helps. It's built into solid rock. And so there's less jiggling. So that's actually, I think that's part of the reason it's in a mountain is to help protect it from seismic motion. It's a great question. Oh, wow, here we go. Yes, sir. So I noticed you have a lot of cavity, like our recycling cavity and signal cavity. Yes. I'm not sure I understand the central frequency of what? Like what's the resonant frequency of the cavity? Oh, I see. Yeah, that's a great question. So the main cavity, the 4-kilometer cavity, actually has a, let's see, the resonant. So the answer is that sorry, I have to think because it depends. The central frequency of the cavity. So the main cavities are kept near resonance, but not on it. It's actually just off of resonance. So the answer is no. It's about the resonant frequency, right? Cavities are tied to the frequency of the light, right? That's why I'm getting myself confused, right? So the cavity's frequency is it's the light is on resonance, right? But then the free spectral range of the cavity is actually it's higher frequency than our sensitive band. Am I getting that right? Yes, the free spectral range, like just the, you know what, I'm getting myself confused. I don't know. I'm getting myself confused, so I'm just going to stop. So it's a good question. I don't know the answer. Yes. Yes. Yeah, no, it's a great question. It's a big, yes, thank you. Great, so the question is, so O1 and O2 and O3 have happened. So those noise curves are real. That's historical fact that you're seeing. The O4 and O5 noise curves are in the future. Those runs have not happened yet. And so the question is, and I think if I can read your mind a little bit, I think you're noticing that there's a pretty big jump from O4 to O5. So how realistic is that? I don't know. So I can tell you why there's a big jump. The reason that there's a big jump is that there's actually a hardware upgrade that's planned. So it's what goes by the name A+. And it includes like a new big 100-meter long filter cavity, and I'm sure some other, maybe some new mirrors, some other hardware improvements. So it is an ambitious agenda to make a real, physical improvements to the detector. And that's why we think that those higher sensitivities are possible, right? Because it'll be new hardware. How long does it take to commission it? How long does it take to noise hunt? Do you turn it on and get that 330 megaparsecs right away? If, with history as a guide, probably not, right? You probably have some amount of, say, iterations, but that's the plan for right now. That's the plan schedule. Yeah. So I would say there's always some uncertainty in the timeline. Maybe that would be a way to say it. Yes. Excellent. Yes, that's right. So I wouldn't say yes. Each peak course. Yeah, I'm so sorry. You're looking at these big line features, I think. Yes. So the lines, that's right. So the question is, what are these line features, if I may? And the answer, or do these line features correspond to individual noise sources? And the answer is yes. Each line corresponds to an individual noise source. Some of them I can tell you offhand what they are. Some of them I cannot. But for example, up around, so I know at 300 hertz, so the mirrors hang from suspensions, right? And those suspensions have resonances. And so the resonant frequencies of those suspensions show up as lines. At 300 hertz are the suspensions that hold up the beam splitter. At 500 hertz are the suspensions that hold up the main mirrors. At 60 hertz, you can see the American power grid, right, has a 60 hertz cycle. Some of the lines at higher frequencies are harmonics of those, again, those violin modes, those suspensions. So yeah, each of the lines can be traced to a specific noise source. So the question is, when we go to future observation runs, do we want to eliminate these lines? Yes and no. Yes and no. So the first thing to say is that as long as the lines are narrow, the narrower they are, the less they interfere with our measurement. So in some sense, we even try to make the lines more narrow, right? You want a higher Q on that resonance, which arguably could make the line taller in a sense. You want to pump as much energy into that line as possible because you don't want it bleeding in to other frequencies. So where lines can be removed, yeah, it's great. If you can get rid of a line, get rid of it. But something like, the suspensions that hold up the mirrors, we're not going to get rid of the suspensions. They're still going to be there. So some of these lines are they're fundamental in a sense. They're very hard to remove. I'll tell you what, I'm going to take one more and then I'm going to go on in the slides. Yes, sir. Oh, they're just not drawn here. Yeah, no, there will still be lines in 05. Yeah, that's the future. Yeah, the future is line free because we use magic to make the mirrors slow. No, it's just they're just not included in this model. Yeah, but there will be line sources in 05. Rest assured. Okay, so speaking of the future, so here's the projected. Well, it's the projected timeline. So I like this plot. I like this figure because it's in units of, well, I guess we saw that on the last slide too. So you can see these things in terms of megaparsecs. So maybe this is obvious, I don't know. But the less noise we have, the more sensitive the instrument is. So the lower amplitude signal we can see, which means the further away we can see, right? So some of the instruments in, LISA is designed to see to the edge of the observable universe or the beginning of star formation or something. PTAs, because they're stochastic sources, will see to the edge of the observable universe. LIGO at the moment does not see the edge of the observable universe. We're observing some sphere around the Earth, right? And depending which source you're talking about, that sphere might be bigger or smaller. So these particular numbers are in terms of how far away LIGO can see a binary neutron star merger. And of course, the volume of space that you're observing scales with the cube of the range, which means that relatively small changes in the range make a big change in the rate of observations, right? And so this is, these are kind of cartoon numbers, but it's supposed to be like how many observations per 6 months or how many observations per year is kind of the scale, right? And so in 03, at the moment, we've published half of 03 and there's 50 published observations so far. We think it'll be close. I think it'll be a little higher than 70, but I think it'll be closer to 100 by the time all things are done. And then if you take these numbers seriously and scale, then you see that, in 05, it's really a lot of sources, right? And you start, if you're getting 1,000 sources in a year, you're talking about like 2 or 3 a day, right? So you're just talking about these things really coming in fast, which is exciting. Do a lot of science with that. All right, so this is probably the slide that most closely relates to the hands-on session. So I just wanted to highlight that something about signal processing. So tomorrow's hands-on session is about data analysis and signal processing, right? So the data as it's recorded is entirely dominated by noise, right? And in particular, right? Oh no, disaster. In particular, right, we have a lot of low frequency noise and a lot of high frequency noise, and we're trying to observe below that noise, right? So if you just take out a data file and plot it, you don't see signals. What you see is noise, and often noise that's like orders of magnitude larger than the signal you're looking for, right? So the process of digging out a signal involves a lot of signal processing. And so this is typically done in kind of a 2-stage process. So the first is a search pipeline. So our search pipelines, actually there was a question this morning. Our search pipelines use a grid of templates. And what they typically are like a 2 or 3-dimensional grid. So they have a parameter space of just mass 1, mass 2, and that spin, the chi-effective, the spin parameter that's most important for determining the waveform. And our searches will kind of search one interferometer at a time over that grid of templates. And so because you're only using one interferometer at a time, you can actually ignore a lot of the other parameters and get away with it, and it's fine. And so we can use that to find signals and identify them and estimate how confident we are it's a real signal and not some noise source. So that's stage 1 is search and hopefully find. And then stage 2 is to do parameter estimation. And so in stage 2, we really want to know, well, what are the masses? What are the spins? What's the sky location? What's the orientation? And that is, Alberto mentioned a 17-dimensional space this morning. At the moment, we don't include eccentricity. And there must be some other parameter he had in mind that I'm not thinking of. So I'm pretty sure our PE right now is over a 15-dimensional space. And you can do a back of the envelope and convince yourself that you cannot make a grid of templates for a 15-dimensional space. It doesn't work. It would take a Hubble time to do the analysis. So actually multiple Hubble times, many millions of Hubble times. So instead, it's a Markov chain Monte Carlo kind of problem. So there's Bayesian samplers that do this kind of parameter estimation game, and we try to figure out, try to solve, create posterior distributions for all 15 of those parameters. Okay, good. So step 1, search. Step 2, parameter estimation. Okay, right. So here's a note on, so our collaboration has been publishing sets of detections in catalogs. So confusingly, GWTC1 corresponds to observing run 1 and 2. GWTC2 is the first half of 03, and GWTC3 is the second half of 03. I guess that's convenient because now, yeah, you catch up somehow. Yeah, somehow you get the numbers to sync back up. Anyway, so So the first, so GWTC 1 and 2 are both published now. Collectively, they represent 50 compact object mergers. And then GWTC 3 is in the works. It's real, well, writing is in progress on, on that catalog. Realistically, it's likely to come out around the end of September, would be a good guess. But wait, there's more because it's, oh no, here, there's no more. This is it for this slide. What else is there? And then there's this website, gwopenscience.org. We call it the Gravitational Wave Open Science Center because we wanted to use the acronym GWOSC, which is the worst word we could think of to pronounce out loud. And that's why we called it that. So these catalogs, all the events, their data, their parameters, all that stuff is available there. You can go and download it and plot it and all that. Here's a snapshot from one of our online catalog. I'm highlighting this just because it's what I happen to do. Here's a snapshot of one of our online catalogs, and there's lots of stuff there. Okay. Okay, great. So I did want to highlight that, at this moment, it's kind of 50 published mergers. So this is really getting to be a rich data set, a rich population. And there's all kinds of things we can learn from it. So this is just a scatter plot, just to say, just to kind of look at it as a set. It does jump out that at least the ones we've seen so far, they tend to be nearly equal mass with some very notable exceptions. And most of them are binary black holes. So again, there's some notable exceptions. So this is a pretty rich data set that's quickly growing. Okay, but wait, that's not all, because they're not just our catalogs or catalogs that the collaboration publishes, but these data are made public. And then there are a few groups in the world who are going through the data and searching. And a few of them are reporting that they found additional signals. So there's this, let's see, there's this OGC catalog. This is led by the group that developed a pipeline called PyCBC. They're at AEI and Syracuse and other places. And they've been pretty consistently searching and finding events in our data, which is great. And then there's this, there's a group out of IAS at Princeton, and they've also been searching our data and reporting new events. So that's really nice to see as well. Yes. The Princeton, I don't know the name of the catalog. This is the first author here. And then there's a reference here, PhysRevD 101. 083030. I don't know if the catalog has like a cute name. I'm not sure. I hope so. Okay, so you can see some data. Great. Okay, great. So I wanted, sorry. So I wanted to now kind of, I guess that was my overview, and now I wanted to transition and show you a few of the kind of exceptional events, some kind of observations, and also talk about some of the astrophysics that we're getting out of it. But I'll start with just kind of the ones that at least I think are sort of the most standout or exceptional. So this guy, forgive the phone number name. So this guy in GW 1905-21. This is the highest mass observer that we've seen, highest mass merger that we've seen so far. So this guy, it's the component black holes. So there's going to be talks. Is it Thursday? I think Dan and maybe Johan, I forget. But I think there's a bunch of talks about formation scenarios. So we're all going to learn about formation scenarios, including me. I'm really looking forward to those talks, so I'll learn a lot. But my limited preschool understanding is that these black holes are large enough that it's not obvious how they would have formed, right? So there's this, correct me when I get this wrong, but there's this pair instability. And so, you have stars, and larger, in general, I think larger stars produce larger black holes up to a point. And then you run into this kind of pair instability somewhere around 40 solar masses. And then there's like, at that point, there's, when the collapse happens, there's this pair instability, which sort of blows matter out of the system, sort of getting that right. And so the expectation is that it's difficult in that scenario to form masses that are much bigger than like around 40 solar masses. But these components had masses that were larger than that. So where did they come from? I don't know. And then of course, when they form, they create an even bigger black hole that's now like, I don't know, 150 solar masses or something like that, which is some kind of record, right? We don't really have observations of black holes of that size before. So that's kind of interesting as well. So that's a neat one. Oh my gosh, so this guy, I can't really say enough about this guy. So actually I don't have to, because I understand Jusha Marka is giving a talk. I'm sure she is going to tell you all about this. But so this is GW 170817. So this was the first binary neutron star merger we observed. And as it happened, it was the standout event. It was particularly close. We were able to localize it to about 9 square degrees, which was really incredible because that's better than I thought we could do. And most importantly, astronomers found a counterpart pretty quickly. So you can see in these images, right? Here's like, here's like a spot in the sky. And then after the merger, you get this bright spot, which is this transient, this kilonova that sprang up. And this got a lot of attention of the astronomical community. It's probably the most observed transient ever, as best I understand. We believe that heavy elements are being created here. It was seen in just about every band. It was seen in radio and gamma rays and optical, obviously. So it's a very exciting event. And then the other thing about it, because it's a loud high SNR, relatively high SNR binary neutron star merger, it means that from the gravitational wave data, we can do all sorts of physics with it, right? And I think I've got a few more slides about that, but you can do things like you can try to measure the equation, the neutron star equation of state. So that's very exciting. You can do with it. You can use this to measure the Hubble constant. I'll talk about that a little bit. So it's just a really standout system. Yes. Yes. Oh, that wasn't the question I expected. How do you get the mass ratio? Okay, so in general, all the mass parameters leave some imprint on the waveform. So yeah, so the chirp mass is probably the kind of the dominant feature, right? That sets the overall timescale of the frequency evolution. So in a way, that's the easiest thing to fit. But all the parameters leave some imprint on the waveform, and so it's kind of a generic answer, so forgive me, but the waveforms are different if you have a different mass ratio. And so it is possible to fit for it. It's not constrained as well, right? The chirp mass might be measured to like 3 or 4 or 5 significant figures, and you might get the mass ratio to like 20%, right? So it's not the same precision of measurement, but of course with higher SNR, you can do better. So at least in principle, the information is there encoded in the waveform, and you can distinguish different mass ratios. Yeah. Yeah, good question. Right. Okay, great. Okay, so this guy is a little funky. This is GW 190425. It's a binary neutron star merger, but it just turned out to be a heavier neutron stars than any that we'd seen so far. So of course, neutron stars are observed in the galaxy, most famously as pulsars, right? So with pulsars, you can, in some cases, you can do pretty good measurements of their mass. So we think we know. So this histogram here, or I should say I guess the gray distribution, these are galactic binaries as measured in the electromagnetic, I think primarily from pulsars, where you can get some measurement of the mass. And then here's the mass of here's the total mass of this binary 1905-20, I got the number wrong, 1904-25, right? So and then here kind of the individual masses measured up here. So at least as a binary, we hadn't seen a binary with this total mass before. I don't think individually either mass is especially stand out, but it is kind of at the heavier end of kind of binary neutron stars we know about. Oh boy, this is one I won't know the answer to. Yes. Ah. Excellent. So yeah, so in principle, we don't know. So I think, oh, sorry. Thank you. Thank you. So the question was, how do we know that they're two neutron stars? Couldn't one, I guess I'm assuming couldn't the heavier one be a small black hole? Yeah, so the answer is yeah, it could, right? So in this case, we don't know. The inference, the statement that they're both neutron stars is really just based on the masses. And so the thinking is that this mass is low enough that under most equations of state, it shouldn't have collapsed to form a black hole. So it's really, so it's not an observational statement that it's a neutron star, it's an inference based on the mass that it is. If it's at the higher end of this, if it's 2.6 solar masses, and if the equation of state is a little extreme, maybe, maybe could nature produce that black hole? Yeah, maybe. Could it be a primordial black hole? Maybe, I don't know. So the answer is we don't really know. The statement that's a neutron star in this case is really just based on the masses. Yes, that's true. Yeah, you're asking, are we really sure that that's a neutron star and not a black hole? No, I think there's, yeah, so the only information we have about, I think what you're saying is correct. So the only information we have about this is from the gravitational wave signal. Could the object in principle be something else? Yeah, I think it could. Yeah, that's fair. Yes.
I wondered maybe, although I don't know if it's actually done, if the deep down would be different, or if LIGO uses some sort of ring down model for neutron stars. I'm not sure.
Yes, it's an excellent question. So in principle, so the question was, can we look at the ring down and tell what's going on, if I could say it that way? And the answer is we would love to, right? So the answer is yes, the ring down of a binary neutron star would be incredibly interesting, right? So for example, now you're getting information about the matter that's there. You're getting really precise information about the equation of state. You can tell if it's collapsed or not. So yes, that information is there. The problem is one of frequency. So the problem is that neutron star mergers, that ring down frequency, the merger frequency and the ring down frequency are starting to get up at the high end of LIGO's band. It's getting, you're talking like 2 kilohertz, something like that, or you're talking well above a kilohertz, right? So where LIGO becomes less sensitive. So at these distances and these SNRs, we're just not sensitive to it. If it were, if LIGO were an order of magnitude more sensitive, or if the binary neutron star merger was an order of magnitude closer or something like this. So someday that's going to be very rich science, but we're not seeing it yet. Excellent, very good. Okay. How many? I'm probably way over time. When do I stop? Just tell me when to stop. I don't care. Okay. Oh, and actually, okay, so speaking of objects where we can't tell if they're a neutron star or a black hole. So this one, 1908-14, there's an object with a mass measured to be 2.6 solar masses. And at that point, it really depends on the equation of state. So this one, we really don't know if it's a black hole or neutron star, because it really could have collapsed or not. And it could depend on the equation of state, could depend on how much it was spinning, could depend on things I don't even know what to ask about. So this one is mysterious, and at the moment we can't tell. Yes. Yeah. That's a great question. I think the short answer is no, right? And so we'll see later. Well, the tidal parameters, if there's some range of tidal parameters you could have had, it turns out the tidal parameters it's harder to stretch a neutron star than it could have been. So it's, the tidal parameters are observed for 1708-17 because it's very high SNR. That's the only one so far. It's a good question. Yeah.
And also, like, if the mass of the black hole is very heavy.
Ah,
it would just be swallowed by, structure. So it would be very difficult to know exactly.
yeah.
If it's true in this case, but it might be.
Yeah, I think that's a great point. Thank you for pointing it. Yeah, absolutely. Yeah, so that's a good point, is exactly that. So I'll repeat just for Zoom that Johan correctly pointed out that because there's a big mass ratio here, right? The black hole has a much larger mass than the neutron star, that the tidal stretch, the tidal forces are less extreme. And so it sort of just gets swallowed as opposed to getting, tidally stretched. Yeah, I think that's right. Okay, and there was a question on the chat. They're here. You can see them on the slide. So the errors are here. So plus or minus 0.08. Yeah, no, these are, I mean, these parameters that are here, this is based on Markov chain Monte Carlo, trying to work out the posterior distribution of these parameters. So these are, I would say these are the measured uncertainties. Yeah. Yeah, these are not made up numbers. Yeah, it's fair. It's fair. It wouldn't be the first time I've put made up numbers in a talk, but in this case, they should be good. I guess we saw this slide earlier, but you can put all these things on kind of a colorful plot. And I guess this is just to highlight. So I guess this is just to highlight that this guy at about 2.6 solar masses falls in what's sometimes called the mass gap. I've learned that that's an overused phrase. There are other things that people sometimes call the mass gap. So this one is really more, actually, you guys will know more about this than I do, but I think this is more of an observational mass gap. We've never seen, again, so the purple guys here are black holes in our galaxy that we see in X-rays, right? So black holes where they have a star companion, they're siphoning off gas, they have a disk, they're bright, they glow in X-rays, we see them, we can measure their masses. And observationally, no one had ever seen a black hole with a mass smaller than about 5. And of course, no one's seen a neutron star with a mass bigger than about 2 or 2.1 or 2.2, something like that. And so there was this kind of observational mass gap where no one had seen an object in this range from about 2 solar masses to 5 solar masses. And this guy, whatever he is, I guess it's this one, must be this one. This guy, whatever he is, seems to live in that range. And then here's, I guess, another merger that sort of had the final guy land in that range. So the point is we're now seeing a couple of these objects in the mass gap. And so that's an interesting place to be living. Oh, here, so I highlighted. So this is the guy, yeah. So this is the one we're just looking at where we don't really know if it's a black hole or a neutron star. Okay, so this is more recently published. These are, so these 2 events are most likely black hole neutron star mergers. And this is the first time we'd seen that particular combination. And there's 2 of them. One of them I think is a little less convincing, but in any case, there's at least 2 reported observations. And so that's fun. So that's a whole new class of systems. You can, so depending on the mass of the black hole, you can imagine getting tidal disruptions in this case. This is a fun simulation where you see a big tidal disruption. Now this is not observational. We're not really seeing this tidal disruption at this point, again, just because of the frequency band. But there are fun things that can be happening with these kinds of events. Great. So I wanted to give some sense of the types of astrophysics that's going on. I saw in the figure there are electromagnetic black holes. Electromagnetically observed. In this figure, the purple guys. So what it means is that you've got a black hole in a binary system, but the companion is not another black hole. The companion is a normal star, a main sequence star, I think main sequence. And it's the black hole is siphoning gas off of that star. The gas forms a disk around the black hole. That disk glows, say in X-rays, and we can observe it. So these are black holes that have been observed in X-rays based on their disk. Sure there's a name for it that I'm not coming up with. I'm blanking. X-ray binaries, thank you. Yeah, so these are X-ray binaries. They're binaries and X-rays. I don't know what you call them. Someone should name these things. Okay, what can we learn from these observations? Yeah, so stellar evolution and population studies. So I am probably the most ignorant person in the room on this topic, so we're all going to learn more about it. I'm so excited. But look, we know, stating the obvious, we know that compact object mergers are the end products of stellar evolution. So by studying how source populations, we learn how stars are born, grow, how they interact, and they die. So you can ask all kinds of questions. So where are these black holes coming from? How are they formed? How many are there? How did their parent stars evolve? Did they come from stars at all? There's a bunch of talks on this, so I'm looking forward to that. And of course, what's great is that right now we're seeing these populations, and so this is becoming an observational science. And of course, as the numbers grow, it becomes like a high statistics observational science. So these are kind of some of the first baby steps that we're taking with this. This is a fit to the black hole mass distribution. I think this is based on the last catalog that was published. You can see, so this bump right here seems to be a real feature. There's some evidence that this bump exists, or at least some feature exists here. So that's potentially corresponding to that pair instability. So the idea is that, you have some distribution of stars. Well, I shouldn't say too much. I mean, well, just correct me when I screw it up. But the idea is you have some distribution of stars. Maybe it's a power law or something like that. Larger stars form larger black holes, but then the largest of them, they encounter this pair instability, they blow off some mass, and there's some kind of pileup here. So maybe that's what's going on. And then there's some dearth here. So maybe we're seeing that, or maybe it's something else. I don't know. But I guess the message is just that in the last catalog population paper, there's some evidence for this bump. So that's an interesting feature. Oh, that's a great question. It would be a small, so let's see, this is M1. So it's a small number. Yeah. Yeah, for sure. Yeah, it's probably not more than 2 or 3 at the most, I would guess. Yeah. Yeah. This, so this is an interesting note. Again, I'm talking about things I barely understand, but this low mass roll-off, so the difference between these two curves, this depend on if you count this 1908-14, this guy in the gap where we don't know if it's a black hole or a neutron star. How do you count it in your statistics, right? Does that count as a black hole? So if you count it or not, you get a different kind of low mass cutoff, say, or low mass roll-off. So that's a tough modeling problem. I don't know how to deal with that. Yeah, which is great, lots to do. We're starting to be able to map out these mergers as a function of redshift. So you can start to get some history information. Yeah, I'm sorry. Yeah, well, it's probably a good thing because we're seeing black holes there. So I hope there's some way to make them. But that's good. That's all good news. Science isn't broken yet. That's great. Right. So yeah, so you do see an increased merger rate at a higher redshift, or at least some evidence for it. Notice the error bars here are really big. This is still hard to do because most of the observers we see are relatively close in terms of cosmic time. But we do know that the star formation rate was higher in the past. So maybe maybe we have some bias. Maybe we think it's likely that we see a higher merger rate in the past, and we think we're seeing some evidence for this. But it's still, I would say, still low statistics here. Let's see. So this has come up a few times. This idea of measuring the Hubble constant. and how that can work. Okay, so so reminding myself of like high school physics or something. So the Hubble constant is how fast objects are moving away, right? As a function of how far away they are. The further away they are, the faster they're moving away. And so to measure the Hubble constant, you need to pick off a measurement of, so V here means the velocity they're moving away, which we really think of as redshift, right? So if you want to measure the Hubble constant this way, you need a measure of redshift, right? Which you can get. So in this case, right, if we talk about like this binary neutron star merger, which had an electromagnetic counterpart, we have this concept of what people call a standard siren, right? Which just means you can use the combination of the electromagnetic observation and the gravitational wave observation to do this measurement of the Hubble constant. And so you can get the redshift in a number of ways if you know the host galaxy. The one that comes to mind for me is like absorption lines, right? You look to see the redshift of the absorption lines, but there's other ways to make that measurement as well. And then once you know the redshift, then you can use the information of the redshift along with the gravitational wave observation to measure the luminosity distance. And there is a degeneracy between redshift and mass, because mass is basically redshifted, right? Because it's redshifted, I guess. I don't know a better, I can't say that better. So there is a degeneracy between redshift and mass, but once you have a measurement of the redshift, you break that degeneracy. You now know the mass of the binary. Once you know the mass of the binary, you know what amplitude to expect. And so you get a measurement of the luminosity distance based on the amplitude of the gravitational wave signal. And so taking those two things together, you've now measured the Hubble constant. Yes. Which part? How do we disentangle the peculiar velocity? Yeah, that's a good question. And yes. I mean, I think in general, that's an important source of uncertainty. I think is probably the answer to that. It's certainly a concern. Yeah. There might be a better answer, but it's certainly a concern. Very good. So this is a plot of Hubble constant measurements. So this is the one based mainly on GW 1708-17. And for comparison, these bands behind it are Hubble constant measurements made other ways, the Planck survey, the Shoes survey. So in general, our error bars are bigger than error bars from other ways to measure the Hubble constant. So gravitational waves are not the best way to measure the Hubble constant right now. We do think it's an interesting way because it's mostly free of the cosmic distance ladder. So we think whatever systematic uncertainties might be involved in these other two, we think many of those systematic uncertainties we can sidestep. So in that way, we think it's a very interesting measurement of the Hubble constant. And of course, the other thing is that right now the number of observed binary neutron star mergers with electromagnetic counterparts is 1. So we're still kind of in the low statistics regime. So it's easy to imagine that this measurement improves with time and with sensitivity of the instrument. Of course, with gravitational waves, it's possible to test general relativity. Maybe that's one of the biggest promises and most exciting things about gravitational waves is so we get these kinds of strong field probes of general relativity. Merging black holes, of course, have fast motion and strong gravitational fields. So it's hard to make comparable systems in the lab. So in that sense, it's a very special laboratory. It turns out there's all kinds of different formalisms. You know, you can test different aspects of general relativity. You can design different kinds of tests. This is one. So the papers about this, like this guy, are pretty long because it's not like one aspect of general relativity being tested or one way of testing general relativity, but a bunch kind of thrown together in a big paper. Here's one that's kind of fun to put on a slide, which is a test of the no hair theorem. And so the idea is that it sounds kind of funny, but the idea is that you just artificially break up the merger and you call the first half the in spiral and you call the after part the merger and ring down. And so what happens is you can use the in spiral part and measure all the binary parameters. And then you know the masses and the spins of the system. And then based on that, you can predict what this ring down is going to look like, right? So in a sense, you're trying to sort of create two different systems, right? You have this in spiral of two black holes, and then you have this kind of ring downy thing of one black hole where you can measure the normal modes of it, right? So this is a case where we can measure the ring down and use that to probe. And so the idea is that before the merger happens, you kind of know the masses and spins, and you know exactly what the system's going to be, and you can predict, for example, that ring down frequency and time scale, and then we can see if that matches. And so here's a plot of that, and let's see, can I get this right? So the deltas here represent the difference in masses and spins measured before and after the merger, and so I think all for a collection of binaries, and then this is kind of the net result there. So you can sort of constrain this difference to that point, and then you can in turn use that as a way to constrain violations of the no hair theorem. So that's fun. Okay. I think they're probably, I don't know which contour these represent. So it's either probably 70% or 90% contours for the limits on these parameters. Yeah, that's right. So each color represents a different binary. And in some cases, for example, if the SNR is a little low, or maybe the merger is out of band, right? So it can be very difficult to measure. So the ring down is kind of pushing the limits of what we can measure right now. So depending on like the SNR and the frequency of the ring down, we may or may not have a good read on it. So yeah, in some cases, these measurements are not very precise. That's right. So I think that's why the authors chose this approach to kind of collect them, try to use them collectively. Okay, I worry that I'm running long. Yeah, so I'm going to, maybe I'll say in one sentence, we can use, we can try to measure tidal deformation in merging neutron stars, which gives us a way, among other things, to probe the neutron star equation of state. So there's some very exciting science there. Yeah. Okay, so maybe we'll wrap up this way. So the IGWIN, the International Gravitational Wave Network, is quickly growing and improving. So it's sort of 3 detectors and counting. There's over 50 published detections so far, and it's probably going to be around 100 after publishing the O3b catalogs. And I think most exciting, the rates are quickly growing. And of course, there's a wide range of science we can do here. And I'll stop right there. Thank you all so much.
Looking at them now. So if anyone had one that's still burning in Slack, please unmute in person or virtually. Go ahead.
Thank you all for the great questions. I really appreciate it. Oh, sorry. Oh, sorry. If you have a question posted in Slack and you would still like to ask your question, then please unmute and ask your question. We are bravely asking you to unmute. Okay, there are hands in the room. There are hands in the room if everyone on Zoom is okay. Zoom going once? Zoom going twice? Okay, I'm going to look in the room. We'll come back to you on Zoom. Yes, let's go back here. Yes, please.
Right, so I have a question about the quantum crisis. But if there are would we expect gas, or I'm just kind of wondering if the ATFS is more individual.
Yes, all of this is excellent. So this is an area of active research. Thank you. I'm so sorry. The question was, you know, if black hole mergers are happening in disks of AGN, could we see an optical counterpart, or might we expect to see an optical counterpart? Yeah, and the answer is maybe, right? The answer is this is an area of active research. I am sure that Jusha is going to have some things to say about this. So Jusha actually worked on a paper trying to model this. And there is a claim in the literature of a potential counterpart, I think to 1905-21. So there is a claim of a potential counterpart to a black hole merger with the idea that maybe this merger happened in a galactic disk. So this is something that people are looking at, and I think actually we're going to hear a lot more about, and I'm sure Jusha will tell you something about it, but you should definitely talk with her about it. She can give you a lot more insight than I can. But yes, it's a very good question, and the answer is yes, it's certainly a possibility. Yeah, please.
Yeah, I don't know if there are any, but do you know if like ask the technical question? Because we talk a lot about size. I don't know if there.
Yeah, it's a good question. I know that there are geophysicists who are really interested in, thank you. The question was, has LIGO learned anything interesting about geophysics? Because we monitor the seismic data and have a lot of awareness of our seismic environment. So I'm not aware of any really standout results. There are certainly geoscientists and geophysicists who have like asked for our data because we do have a pretty complete array of instruments around the sites, seismometers, accelerometers, tiltmeters, all these kinds of things. So there are people who are interested in using that data, but I'll tell you, there's a really interesting connection. There's a really interesting story about Newtonian noise, which is the idea that for not for the current generation of instruments, but for a future generation of instruments, it is possible that, you know, right now we talk about seismic couplings, and it is possible that with future instruments, when you have like seismic motion in the earth, rather than coupling through like physical contact with the ground, that it could couple to the mirror just from the gravitational field of the earth, right? Which is a very hard thing to shield against. So there's actually there's a really interesting story, interesting research about how you deal with that. Yes. Oh, that's larger. Yeah, that's larger, but fortunately it's very low frequency. Yeah, so we get a tidal, I mean, you know, the mirrors are 4 kilometers apart. So the tidal forces between 4 kilometers are significant, right? So not even, I think even without the Earth's, anyway, I don't know the details, but the answer is I know that, yes, it's actually much larger than our measurement, but it's out of band. If we were doing like a 24, you know, a period of 24 hours, we'd really have a problem, yeah. Well, Lisa's not on the Earth, right? This is one of the many advantages you get to going to space. Right, exactly. Yeah, among other reasons, but yeah, yeah. Yes.
I have a question related to that.
Yeah.
But I read a paper that and they were suggesting that the high mass event that maybe was not really high mass, but it occurred very close to a supermassive black hole, and so the mass was sort of artificially gravitationally redshifted. Okay, I wanted to ask you if there's
Cool.
an opinion on that, but I see from your face that
well, no, I apologize. You're more informed than I am, so it's the first I'm hearing of it.
Sure, I will find it somewhere.
Yeah, but yeah, but
the largest event, I don't remember the name.
yeah,
The largest-
1905-21.
Yes.
Yes.
Yeah. Okay, but it was a very interesting paper. I thought maybe there was an opinion of looking for gravitational redshift in the mass, and not only of cosmological redshift.
Yeah, I mean, I don't have a problem with that. It sounds like a very interesting paper.
It's a similar idea where if this merger was orbiting, not just for gravitational redshift, No, it's a tracer of the environment. You can think of that.
That's true.
Opportunity, yeah.
One more.
Yeah, oh, and maybe, and I'm gonna sneak in sort of an announcement. So for the hands-on session tomorrow, I think it's gonna be a lot of fun. You're all gonna work with some LIGO data. For some of you, maybe that'll be new. I just wanted to share, if you have like headphones or earbuds, bring them, because it's not important if you don't, no big deal if you don't, but if you have them, there's one activity that uses headphones. Okay, so yes, and then a question, and then we're done.
Yeah.
Okay, great.
You did mention that there will be degeneracy between the and the non-strip.
Yes. Say again?
How do you separate them?
Yes. What's that?
Degeneracy between mass and
Oh yeah, sorry. Yeah, the question was, there's a degeneracy between mass and redshift. How do we separate? So how do we separate them? So most of our observations, let's see, do I know the answer to this? Yeah, we have to measure. So let's see, how is that degeneracy broken? So the degeneracy only occurs like in the chirp mass, right? In the F dot, okay? So I think that if you bring in more information, then you could potentially break that degeneracy. Seems possible.
I was mentioning in the Slack that I think Wednesday we could go over these measurements of standard siren calculations, because what's happening here, I don't know if you remember from my lecture, you could write the strain in terms of frequency derivative. Each of them gets a different factor of the redshift, right? So you really have to measure both of them, this factor of the redshift, multiply that distance, and turn it into a luminosity distance. To get anything more than luminosity distance or the chirp mass, you have to measure a redshift. But I think we would all learn this much better if we spent a little time just writing it out, maybe on Wednesday.
Yeah.
So, proposition.
Yeah, that sounds good. I'll learn something.
Anyway, so I think we should give Jonah another round of applause.
Thank you all very much. That was very fun.